Thanksgiving weekend. Week with number of students that are here. All my faithful students. It really pains me knowing that most of you will fail. Can you still hear me? Okay, good, because I think the phone won't pick it up. My, what a lovely group of students I have here. Oh, they're so smart. All right, so next week you have, I'm trying to think, it's right after, is it the following week? I think it is the following week, is that the, what is this? Do we have our thing on the 3rd? Is it the 3rd? Okay, all right, so next week is last week. Okay, so. And I did post homework 8. No, I posted homework 9. There's a homework 10. There's a homework 11 that is all the answers are given, so that one you'll get credit for. Okay, so like I said, for these problems here, the major issue is going to be with really getting the correct sign. And since Rachel wasn't here last week, okay, let me just quickly remind you how to get the sign things out. So there's different ways of doing it. I showed you the card, but the one way that we're going to do it is you don't have to. There's other ways, but I showed you this last week with the fingers and hands. So for this system, okay, and you have to pay attention to what we're talking about. So this is a charge moving through magnetic field. First of all, you've got 2 hands. Right hand is for charge. Positive. Are you sure? Are you positive? Left hand is for negative. But I said that you can flip-flop them sometimes because sometimes it gets really weird to move your hands. And I also told you that on your paper, you can also rotate your paper, and that might help you get the correct directions. But anyhow, get back to this. He went that way. Index fingers is always the velocity, which way the charge is going. So that's going to be your velocity vector. The middle finger, right? So from now on, you won't give people the middle finger, you'll give them the B finger. This is the magnetic finger. Okay, that's the direction there. Okay, magnetic. And then F is for force. So you got that. And then all you have to do when you do when you see this next homework, number 9, you'll get a better idea of what I do. Primarily, what will happen is I'll give you some type of information about the object, and I will give you, information. Sometimes I give you a picture. But this is what we're going to look at. Think of it this way: when you read the question, I'm giving you certain information. So let's say in the question I told you that the magnetic field vector, which we use to be, by the way, what unit do we use for magnetic field? That is what? For the unit? Name that for a car or a person? Tesla. Okay, so a lot of times it'll be in micro Tesla, so you just have to convert. But I have to give you some information about this. I'll give you a number, and this calculation here, basically, once you got the numbers, you just put the numbers in. It's the direction that you need to get. And one other thing I said, we're not going to worry about the angle. And the only reason you need to know the charge is to know which hand to use. So let's say I do this and I say, boom. So I just drew a circle with a dot. Okay, circle with a dot. In a circle with an X, we use that to indicate the K direction. And for us, we are now moving it from the XY plane into the Z plane, which goes in and out. But the Z plane is also known as the K hat direction. But instead of putting down K hat, we can also use this symbol. So the analogy we use is shooting an arrow. So if you saw this, it's like the tip of an arrow coming towards you. Therefore, we're saying that the magnetic field is coming out of the board. So that's what that means. If you were to see one with the X, so there's some that have the X, that's like you're looking at the feather. If you're shooting at something, you're shooting something into the board. We'll get into that a lot. So that's one direction. Then I have to tell you something else. I can say, okay, the velocity vector. I'll do the force vector. Okay, so here's the force vector, and of course that's got to be in newtons, and I got to give you some idea of which way it's going. So usually in problems I say it's moving from the bottom of the paper to the top, or I might say it's moving from left to right. In this case, I'm going to give you an arrow like this, so it's moving to the left. One other thing I have to tell you that's very important is I got to give you the charge. Okay? So let's say that this is an electron. So this is a negative Q sub naught. Okay? Or I could put a negative E, that's what we use for electron. So you've got the charge, you got the force, you got this. The one thing that we're missing that you should be able to get from this is A. You've got a velocity vector, V, and the question is, what is its direction? So, first of all, whenever you do these problems, if they tell you what the charge is, then automatically figure out what hand you're going to use. If it's negative, oh, I should mention this, I usually do this. Okay, so if it's negative, then you should know that you should start off with the left hand rule. By the way, in physics, you probably will very rarely see that there. They always talk about the right hand, but you can also use your left hand. Okay, so I got my left hand. Now what I got to do is I got to figure out how I'm going to orient my hand so that it matches this. And you can do it any way you want, but here's what we've got. I'm not going to give you the middle finger. I'm going to give you the B finger. I'd have to take my middle finger, put it into the board. Now, I've got my velocity. My thumb is the force. Now, here's what I was talking about. My middle finger still is into the board. But my thumb, my force, you see how I have to kind of, on the whiteboard, this is kind of hard to do. On regular paper, you can just rotate your paper. So I can go ahead and use my right hand for positive charges. Look what I did. Put my middle finger into the board, my thumb, okay, and you gotta remember, you gotta keep that. Okay, there. My finger going into the board. My thumb now aligns with this very easily, and my index finger is pointing up. And this is a positive charge. Where we go. So because I'm using the wrong hand, I have to change the direction. And so the correct answer for this is it would be going down. And actually, I should mention one other thing about this, if you understand. If it's in a large magnetic field, this force here, okay, is always going to be acting in a sense towards the, it's always going to be acting towards the left initially, but this charged particle is going to start to move this way because of that force. And when you get something in a large magnetic field, what you basically start getting is a circular orbit. So this is just at that moment in time that we're looking at the forces and all that. And like I said, if I gave you numbers for that, you plug it in, and you go like velocity, you see meters per second, blah blah blah, and it would be a negative number, meters per second, j hat. So I just wanted to remind you of that because we will do more of this. By the way, I'll give you one more that involves this to show you this. So let's say that I'm going to have B. Here's B. Okay, magnetic field. But this time I'm going to have it pointing down. Second thing I'm going to do is I'm going to tell you that the velocity vector for this is going to the right. And then I'm going to tell you that the charge experiences the force. So the force acting on this charge is going to be like that. So it's going into the board. So notice this situation here where I give you these different directions. Okay. I never mentioned the charge. So what you're going to have to do is take your right and left hand, see which one will align with this, and that will tell you the charge. So since we don't know what the charge is, just take a hand, and if one hand doesn't work, then you know it has to be the other. So now one thing I want to mention real quick, because this time it's different. I should mention this. Remember that the magnetic field is related to a bar magnet. Okay, that's how we do it. Technically, if you were to draw a bar magnet here real quick, okay, this would be north, this would be south. Okay, because the magnetic field always comes out the north and always enters the south. By the way, you can actually do it with this. I didn't mention this, but because this is coming out of the board, this is like looking at the bar magnet straight on. You would be looking at the North Pole. That's what would be sticking out. Okay, so we got that. Now, here's what we're going to look at. What is the charge? So I'll use my right hand. Let's see, yeah, because that's pretty easy. My B finger going down, index finger going this, and look, my F force is going this way. So this matches perfectly. Because this matches perfectly, it's my right hand, that tells me that this is a positive charge. Sweet. There we go. All right. And I'm getting you all set up for this because that was for a charge, a single charge. Oh, don't forget. So you got a magnetic field, okay? So the question is this. What happens if I have a neutral particle and it goes through the magnetic field? What does the magnetic field do to it? The answer is nothing, right? The magnetic field will act on charged particles only. So one of the things to note, that's why some of these air humidifiers, they generate a static charge on the dust particles, and then, well, that's using electrostatic, but using a magnetic field, you could do this same thing. If you had a dust particle that had a charge on it, you had a strong magnet, you could actually start moving that little dust particle. So that's one thing. Neutral particles, there's no effect. You can go whichever way it wants. Another one to remember is this. What if this velocity vector and magnetic field vector are both parallel? So it could be, hey, we got magnetic field vectors point down, and so I could have it where I could have the velocity vector going down, charged particle, okay? So when both vectors are parallel, the deal is no force. Even if it's going this way, no force. That's why all three vectors have to be perpendicular. Okay, so those were some of the key things to note for like the closed book portion of the exam. Did that. Okay, got this. And we showed you that. So, in some of these problems now you should kind of like understand. So real quick, just looking at this one here, you haven't seen it. You can tell, well, I should mention this, just because this is an X, it doesn't mean that's the magnetic field. It could have been the force or whatever. But I know that the way this is set up, that the magnetic field is going into the board. And the thing is the idea is you're shooting a particle and it's going to go through the magnetic field. And we want to know which way is the force going to act. Once that force starts acting on it, it'll continue to act in that, and you get this circular pattern. So the question is, I don't give you the charge here, but you can see which way it's acting, because right here, here's the center, right? So when we studied centripetal forces, there's something that's kind of like pushing it always towards the center. So right here, the F vector would have to be this way. If I take my right hand, okay, so I don't know what the charge is. If I put my middle finger into the board, okay, here's my index finger, okay, it's going this way. But notice the F, the force, would want to make it go this way. That's what you see here, right? So this must be the positive charge. This must be, once again, magnetic field going into the board, charge particle going this way, boom, boom, this way. This is a negative charge. I'll tell you one place where you kind of see this. You've seen this? I'm assuming you've seen this. In all these colliders we have, they, especially in the old days when they used to take pictures of it, you'll see that particles you collide together, they break up into other particles, some of them charged, some of them not charged, but they'll form a spiral pattern. Okay, that's one of the things. And which way the spiral pattern is twisting tells you what, if it's a positive or negative. The size of the spiral is telling you the mass. Real quick, because if something's more massive like the proton, it's more difficult for the proton, to change its motion. So it creates a larger circle. Electrons have virtually no mass, so it's very easy to make them quickly change their direction. So we use that mass spec. Number two, now one thing I know, this vector here, it is not parallel to the magnetic field vector. So I know that this particle here must be, so your choices would be positive charge, negative charge, no charge. Right, no charge. It just goes right through. Okay. So that's all getting accustomed to doing your hands. And this is just like math. The math part is easy. It's the direction that really throws people. Okay. Now, here is the thing that we're going to find out. We're going to get into electromagnetism. Same thing. It's going to be the same thing, but here's the difference. The difference is we are going to have charges move. Okay? Charges are moving, but they're going to move through a wire. So that's it. So normally, the way you would think about current going through a wire, you would think about the flow of electrons. But, I said this several times now, it turns out because of history, they like to talk about the flow of conventional charge. I see. So if it's conventional charge, I can tell you it's conventional, which means it's the flow of positive charges, which means that somehow you're going to use your right hand, okay, but depending upon what the object is, you use your right hand in different ways. So just keep that in mind, and I'm not going to try to trick you out of this. By the way, if you wanted to go with electrical charge, electrons, you just use your left hand. You get the same result. All right. So what are we trying to do here? So starting off with the simplest thing that we can do is you start off with a nice straight wire. And it turns out, most people would not notice it. A nice straight wire. If you pass a current through the wire, that is a charge flowing. So remember this. Remember how we had a charge moving through a magnetic field, right? Now we're doing this. We're going to have a charge move, but when it moves, it will also generate its own magnetic field. So that's important. So there's always that relationship between charges and magnetic fields. So the idea is, here's a piece of copper wire. I'm telling you that the conventional current in this wire is going like straight up. By the way, this is a top view, so you're looking down on the wire. That's why you got the current, which is going to be positive charges coming towards your eye. And the question is, what is the magnetic field around that wire? And there is a way to find it. I think I got some pictures of this too. And what it is, because we're doing conventional current, we're going to use our right hand. This time, here's what you're going to find out. We're going to, instead of having that weird configuration, we're going to have it where we basically have a thumb and curled fingers. That's going to be the secret to this. And what you do is, if you were to put your thumb along the direction of the current, so current's going up, my fingers would wrap around this. Now, if you're doing this on paper, notice my thumb would go up. But if I'm going to curl in, see where my fingers, all my fingers, aren't they going into the board? Now, you have to remember this. If they're going in here, then technically, on this side, they're coming out. Now, what we're doing here, this is the magnetic field you're looking at. So you have to imagine that half of this is like the board here. Okay? So because it's going in, there's the North Pole going in, behind the board, there's where the North Pole would be. Coming out of the board would be the North Pole. And then if you were to look this way across, you would see like a little bar magnet, south on this side, north on this side. And we can actually see it. And here's the trick that we do. I think I have it. Let me see if I got a picture of this. We can see the magnetic field. We can measure it. What do you think we first kind of like use to measure the direction of the magnetic field? How would we get our bearings? How would we find our way? What was that? Right, a compass. So here's what will happen. You go here and go here and real quick. Yeah, I forgot to tell you this. I forgot to just show this real quick. The Earth is going to undergo a magnetic reversal of poles. Okay, it's happening now. Probably your kids will live through it, where it's pretty chaotic, and then eventually the poles will flip flop. Okay, that's what that is. By the way, when I give you this on the exam, you should be able to draw exactly. I'll provide the colored crayons. All right, yeah, because I just forgot about that. And I guess I also mentioned it real quick. Okay, since I forgot about this apparently last week. Okay, so right now, see, this is what I said about the compass. The north end of the compass will point this way. But look at the magnetic field line. It's going into the Earth. It goes into, this must be actually a magnetic south pole. This is a magnetic north pole. And then whatever, so many 100 years, whatever, it's going to flip by. But real quick, this is what I wanted to mention about this is one of the things that makes electronics possible here on Earth is Earth's magnetic field, okay, it protects us because now we know that the sun's sending off these charged particles. When they hit this magnetic field, will they experience a force? Some of them get trapped in here, some of them are diverted, but this is the thing about this. They're basically concentrated pretty much at the North Pole and the South Pole. And when they do reach the atmosphere, they start to produce those nice colored lights, auroras. Okay. The problem with those auroras that you have to understand is that they're charged particles. Sometimes they're very strong, and these charged particles are looking to get to the lowest state possible. That's Earth's surface. And it happened over 18 something where we had really strong mass ejection particles. And back then they were using the teletype. They used to be able to send messages without even using batteries. Sometimes the thing would spark. Okay. We've actually had issues early 2000, I want to say, and in the 60s, where the electrons go in, the charges go into the power grid, especially in Canada. Those wires you all see, the thing about those wires, it's not like one company owns the wires. Okay, they're shared with everyone, so it's like national highway. So Canada's grid, electrical grid, is in with our grid, and so when the charges went there, it overloaded the breaker. New York overloaded the breakers. Back when the lights went out in New York, and nowadays they have special things. We have like little triggers where they see something like this happen, they'll just shut it off. Because if you don't shut it off, it destroys the system. So that's fine. One last thing to note, we have a satellite out in space that looks at the sun all the time because it's looking for these mass ejections. And the reason why we gotta know if they're coming is out here, we've got things that are very sensitive to electrical charges. What are they? Right. So all those satellites, if we do have mass ejection and we did not turn them off, they will kaput. I don't know if you've ever seen one of those movies where they use an EMP, electromagnetic pulse. Anything that's on, it just shorts it out. So those are some of the things that we really have to worry about. That is a major issue. And then this is how we get protected. Okay, so here we have it. Okay, apparently I don't have the thing with it. Okay, but this is what we would do. You can see the iron fibers going around here. Another thing we like to do, we put little compasses there. And so you see little arrows in the direction. That's how we know which way, how the magnetic field is going, is this in a North Pole, South Pole? That's how you know it. But you can't see the iron fiber. You need a compass to determine what the polarity is. Okay. So here's what's going to happen. When you're doing a problem, they have to give you some information about what the device is. So this is going to be basically a straight wire. Now, once you know it's a straight wire, and there's different ways of doing this, by the way. So, for example, I may have it going straight up like this. I can have it going this way. You just always apply the same rule. So, if you got this, you're doing this, you would be able to answer the question as to what is the direction of the magnetic field here and here, if it's going in or out. If you're looking above it, is the current coming towards you or is it going away, the conventional current? You can do all that. So this is all about getting the direction of the magnetic field. But this does have a magnetic field strength. And the question is, how do you figure it out? Figuring it out is real easy. It's just getting the directions correct. And so, that non-knows. In that folder, real quick, I don't know if you saw this, but I have, not there, okay, I saw it before. Where are you at? Formula. I put down all, there's the formulas we'll be using real quick. This is in your folder, okay? So you can see some of the things, it tells you what the units should be, okay? Right now we're doing long straight wire, okay? And then I've got it set up in different ways, what you're looking for. Here is the actual formula down here. So you should be aware that you have that. Let me go back to this, and where are you at? I got here. So we got all this, you can't read this, but here is the formula. So at times when you look at B, when we did that first formula on charge going through a magnetic field, I had B external. That's an external magnetic field. This magnetic field, B wire, this is what the wire is creating in terms of magnetic field. One thing to note, you've got this special constant here, which is magnetic permeability of free space. So here's that number. You should be thanking me now because I'm not going to have you, remember on the closed book portion of the exam, I say, hey, what's the unit for blah, blah. I'm not going to have you remember that. I want you to be surprised when you see it. Okay, but that's just a special number. Current always has to be in amps. Right? All right, so depends on how you're going to do this, but always remember this. If you're just using a regular calculator, anything that's in the denominator, I would tell you, put it in parentheses. Oh, by the way, another thing to remember now, if you're not using your EE key, you got anything in scientific notation, you want to enclose it in parentheses. Because if you break things up, then you get the wrong answer. And I've already figured out what those answers should be. You're measuring the distance from the wire. And you do it in meters. So all of this is pretty easy to figure out. You got that chart. It is the direction that I wanted to look at. Here's the one problem with this. It turns out that the magnetic field of a wire, relatively speaking, it's pretty weak. Okay? You do have to worry about it because there's different things that can happen with wires. So you have, let's put it this way, they don't have coax cable hardly anymore. We had coax cable. That was a piece of wire and it had metal around it. It turns out that if wires are too close together, then their magnetic fields can interfere with one another. And with electronics, TVs, that would be an issue. So these are pretty weak. So we can up it. We can get something that will generate a stronger magnetic field. And it's this. So this is a loop. Okay, so it'll tell you, hey, you got, a loop, loop of copper, whatever. Okay, you got current flowing through it. So this becomes a little bit more trickier, okay? And here's the first thing to know. It turns out the strongest part of the magnetic field will occur in the center of the loop. Anywhere else, it's weaker. This is the strongest part. Our formula is going to deal with what is the magnetic field strength here and what is this direction. So you have a loop. Okay, so let me give you, all it is just a single piece of loop. So like I got this here. Okay, and someone's, what are we doing? Oh, I was going to say you're on your phone, but no, your phone's not okay. You're just spaced out. That's what happens when you don't take your medication. So what is this? Well, when I was a kid growing up watching TV, it would be, I can't pronounce your name. I see Rachel. I see he who will not be here long. I see Romper Room. I don't think if you talk to your parents, they probably would know what Romper Room is. Okay, TV. Okay, but here's a single loop, and you don't have to have a single loop, but right now this is what it's dealing with. And here is what's going to happen. So I'm going to use this marker so that you understand I'm going to be outside light. But you see where the first loop, you see where it's got the X, so the arrow's going through it. See what I'm saying? Okay, so it's like this, going through the loop. So that means the side that's inside the board is a north pole, the side outside would be a south pole. So if you ever see this, it's like you're looking at, if I drew a box here, I would have the letter S for south pole. Here I would have a box and would have the letter N, because you're looking at the bar magnet straight on. So that's one thing. Okay, students don't have any problems with that. So the question is, hey, how do you get basically this direction? You know, how do I go from that way? All right, so this is the way you're going to do it. Since it's going to be conventional current, the secret, maybe it'll be a little bit easier for me to do it this way. See, I got it kind of like a loop there. We're going to use our thumb and our fingers. Like in the last problem, the thumb was used for direction, right? Now what we're going to do, see how I'm taking my thumb and going along the loop? So my fingers are going inside the loop. Okay. Therefore, that's how we're doing. We don't care about going this way because that's going to be weaker. If, see what it says there? Now, here's a little trick about this. Okay, I'm saying it's coming out here, right? That means it must have entered here and went this way. So that would be going like this. See, that would be the same thing, right? But if I take my fingers and I got my thumb here and I go, how do they curl in the center? You would notice that they're going to curl out. That's why it's got the point there. So the North Pole is coming out. So that should be relatively easy to understand. We're still using the thumb for current, the fingers for the direction of the North Pole, because that's what the fingertips represent. There is going to be one thing that will confuse students big time. I keep telling them, do it this way and you'll get it right. And here's what I'm going to do. And actually, let me turn on the light here. I got it drawn on the board. Where? Here it is. So here's, first of all, we've already established right here that the magnetic field was going in, right? This is how it looks. Okay. The question we want to know, if we were to look at the loop on the side, rotate that loop. Okay. And this is going to be the secret to doing this. We're going to rotate it using our pinky finger as the pivot point. Okay. So in other words, I've got it like this, okay? And of course I can't really do it kind of like this. So here's my pinky on the board. Yeah. Okay. I got one of these too that tells me, it says, oh, what am I saying? It says, remind me later. Remind me tomorrow. But it comes up, pops up and says, remember, students are failing. So, all right. So let me get this part, because this is the part where students will transcript. I'm trying to do this loop where you rotate it like this. So what I tell students to do is, I'm going to kind of this way because I'll make it easier. This is the North Pole. Use your pinky finger here to be the pivot point, and you're just going to rotate your hand up. Okay. So this is like looking at the loop from the side. Okay. So we're not doing it like this. We're just using that part. So the other one, when you look at that, so initially, here is the loop, and here's the loop. Here's the magnetic field coming out, so the North Pole will be there. And when I say, what does it look like on the side? You rotate your hand like this, and you can see how matches that. So that's what I want to show you. That's where students will make one mistake. And here's what this is trying to show you. In the center, the magnetic field lines are closer together, indicating that it's stronger here at the center. It spreads out when you get away from the center. Yeah, let me kill that. There we go. Okay. Also, what I did is I put a bar magnet here. Just remember that these magnetic fields are related to a bar magnet. Okay, so that's how you can see it that way. So this is like the tricks. Like I said, direction is everything. That's the thing that'll screw students up. Because if I ask you what is the strength of the magnetic field in the center of that loop, what would happen if you go through, okay, this is some of those instructions here. Okay, here is the formula. So now, and once again, if you go to that one chart, you got all that stuff. If you go to this chart and you know that you have the magnetic field, magnetic field for a loop, if you go down here, magnetic current carrying loop, I've got the different formats that you should do this. And once again, whatever digits I put here, you should keep all the digits, don't do rounding. And I make whatever notes here. Here's the original formula. So notice, once again, small number. Like I said, if you got this, you're not using the EE key, boom, put that in parentheses always. This would be in parentheses. Depends on how you want to do it. But you're going to divide by the radius. So you sometimes have to be careful because they may give you the diameter of the loop. Otherwise, everything's there. And when you look at this, it turns out that this will be a stronger magnetic field with respect to the same current. Things are a little bit different, but here is, you just don't have to have one loop. So I have one loop, N would be 1. I can have 10, whatever. R here is the radius. And so one of the things that you can do is you can manipulate this to make a loop very strong, the magnetic field strong or weak. I think one of the homework problems asks you to figure out how many turns, or for a solenoid, maybe for a solenoid, but how many turns you would need. So the formulas are easy. It's the direction that kills people. Now, everything I'm doing here, I'm kind of going over this kind of quickly here, because the most important one, okay, if you want to look at something that we use a lot, it's really important, is this last one. And that is what we call a solenoid. And the reason why the solenoid is so important is in the center, it will generate a very large magnetic field. compared to everything else we've seen, you want to generate a large magnetic field, use a solenoid. So this looks basically like the same thing as that loop, where you have a whole bunch of loops. It's right here. Yeah, right there. See that? It's all copper. By the way, it's got a varnish on it. This can't be just pure copper because it wouldn't work. It has a varnish on it to keep it isolated. But this here will generate a much larger magnetic field than what we've seen in the previous things. Real quick, I'm going to do a little survey. How many of you have ever made an electromagnet when you were in school? I mean, you did this in like 4th grade. What it is, maybe I'll describe it. Maybe you actually didn't know what it was. Back when we did as kids, we had the big battery packs, like the big ones, like they're 6 volts. And what you do is you take copper wire, okay, that's it's insulated. You wrap it around a nail several times, attach it to there, and the magnetic field, it magnetizes the nail, and you can pick stuff up. There you go. And then you turn the current off, and everything drops. So in junkyards, they sometimes have an electromagnet. They do. Okay. This is the same thing. The thing is that you find this in a lot of things. Matter of fact, probably the closest. Sometimes you put this in your ear. See this one? Wait, sheet right here. Right here. Let me show you how this fits in your ear. Okay. Actually, you put this in your ear. Okay. So what I'm talking about is your earbuds. We're going to discover that if you look at it, what it is very, very fine copper. Okay. And remember, I told you when you put current through the copper wire, it generates a magnetic field. But there's one other thing in your earbud, and that is it has a little button there. It's one of those ceramic magnets. And the ceramic magnet has its own permanent magnetic field. And you got this thing here, and if I put in a current going one way, this becomes a north pole. And if this is a north pole, but if this was a south pole, it want to go in. And actually, the coils actually surrounds the magnet. So what you can do is you can make that little coil vibrate like this. But then it's attached to a membrane, and it moves the air. So that's how you can generate sound that way. And of course, everyone knows that your earpiece there is also a microphone. But because if you talk like that, it'll generate an electrical current. Why? But it does that. It's a crappy microphone, but it does do that. So this is why solenoids are really important for that. A lot of different things. If you have a car, okay, I don't know if you ever had a car when it starts to die out, it's hard to start it. Why isn't it starting? It's because it has a starter, which is basically a solenoid like this, and the solenoid is designed to give it a high enough voltage to give it a spark. And once it's going, then they'll run. Hey, guess what? Well, nowadays you don't see it as much, but remember your cards, your credit cards and all that? Remember how they have that little plastic strip and they have to put information on that? So, and this is also how the old cassette tape players also. Do we need to take a break so you can close your eyes? Okay, you just look at your eyes and okay, so the deal is, in the old tape players, they had one of these really, really small, but it looks like the credit card thing. And what it does is that strip that you see is a piece of plastic, but it's embedded with iron. And it turns out, I said last week that you can magnetize like a screwdriver. Well, what it does this time is the iron is in all different states. It's not magnetized. You come over to the thing, and if this is a north pole, okay, the piece of iron in here, that's going to be a south pole. And then the next piece comes over. If that's still north, this will be south. So you can change the polarity there, and you can set up these ones and zeros in a sense. And then that's the information. That's why I told you last week, one thing you don't want to do with cards like that is now that we have these really, really strong magnets, you don't want to put it by your card because you can wipe out the card because you reset the magnetic field. Even the VHS tape, that's just a bigger, you can, now with magnets, you can wipe them out. So that's how you can encode stuff. But how do you read it? Guess what? You use another solenoid. Because now that this is a north pole, when it comes into the loop of the wire, boop, it sends a little current. And then you flip-flop it, sends a current. That's how you read it. Keep going. Ready for this? Okay. We'll find out. If you ever look at the roads, especially around certain intersections, you ever notice they got these weird circles that they put in? Okay. What it is a big piece of coil. And we're going to find out why that's important is the coil already has a certain magnetic field, but if a piece of metal, you put a piece of metal in here, it'll change the magnetic field strength. Okay, so it changes the current. Okay, why do they do it? They want to see if the car is there. Because if you get a car there, then now, okay, let's change the light. So there's lots and lots of things that we use this year. Solenoid. By the way, if you're in lab, we talked about solenoids as being inductors. This is also an inductor. So a lot of uses there. So the question is, how do you do this one? Doesn't this look pretty much like the previous one, the loop? So once again, remember, take your thumb, in this case, the current is going around. So in the center here, I can see that what's sticking out on this side would be the south pole. What's going into the board is a north pole. Anything for that? What about if you did a side view? Okay, and so I have to make sure I have the wires around it because here's what you have to understand: this current is going around this thing this way. So if I did it this way, then I rotate my hand this way. It's the same thing. So north would be pointing out this way. Basically the same thing that we did for the loop. So for the solenoid, here it is, same thing. I put my north pole in here, rotate it. So this side would be north, that would be south. So that's how you can read the directions. And let's see. So, like I said, calculations of the numbers, easy. Direction, that's a pain. So here is our formula for the solenoid. And once again, same thing, like a number. By the way, N now, we have a solenoid. You could have one that's got maybe 10 loops, 100 loops. Some of them got thousands of loops, okay? And I should mention this. Another place where you see solenoids, we'll find out that's very important is if you're charging anything, you know that the current from our outlets is what type of current? What was it?
AC.
AC, right. Okay, you remember that because you thought to yourself, let's see, I'm never going to get an A in here. Maybe I'll get a C. Very good. That's very good. And so the deal is, you can't use that to charge your phone because we have to convert it to DC. And he says, I got a D. There's no way I'm going to get a C. So the way you do that, you know, we talk about the brick or what is really what's a transformer. The thing is what? The transformer, know what it really is? It's basically a piece of metal, okay? There's a coil over here, a coil over here. So you can use two solenoids to change voltage and current. So very, very important. The only thing that's more important than this is who? Who?
That's all right.
You got it. And I got it on tape. Okay, we got that there, and I'll put you to go through some of these problems here just to show you the, like I said, direction is everything. But I realized, what did I realize? What did I realize? I realized there's something I wanted to do. What was it? It was, this is one, but now there's something else I wanted to do. Something about this. I know I have something that I didn't bring with me. Oh, that's right. Okay, so the next 2 classes, I'll be showing you items, okay, that incorporate what we're talking about here. Here's the deal. They can appear on the closed book portion of the exam, but the only way you're going to know about it is if you're here for lecture. Yeah. Okay, so what I'm going to do is bring us 2:30. Let's make it about 2:50. We'll be back, okay? And I got to get these devices, and we'll get into this. I'll show you directions. Like I said, it's not bad. It's just the directions. By the way, what? You want to clap? Yeah. It's okay. I can dub in the clapping. Let's do that. Oh, and Rachel,